Hello, this is Sujin from KAIST. In this session, I'm going to introduce our system named SailsTrain, which accelerates model training in multi-cluster settings with consumer-grade GPUs. The field of machine learning has shown incredible growth driven by the development of complex models. Since training these models require massive amounts of computing power and memory, distributed training has gained attraction. Thus, large companies such as Meta and Microsoft have built massive GPU clusters to train large models. In addition to industry, there have been an increasing demand for distributed training in academic environments. However, academic environments typically face budget constraints, which limits the resource available for such training. So it is common to use consumer-grade GPUs and slow internode connections. Although their performance might be moderate compared to their data center counterparts, they provide a cost-effective solution for academic needs, as the consumer-grade GPUs are 10 times cheaper than data center-grade GPUs. However, such distributed training poses a non-trivial challenge when the network bandwidth is insufficient. Let's look how a distributed training process goes with data parallelism. In the forepass, each GPU or computing node feeds a training batch into the model to get a prediction and loss. Then the backward pass calculates a gradient with respect to the model parameters using backpropagation. After the backward pass, we need to exchange the local gradients in each node to aggregate gradients. And we need to run model optimizer to obtain new model version from the aggregated gradients. Here, when the network bandwidth is insufficient, the communication becomes a significant bottleneck and stalls the training process. But how much bandwidth do we need to prevent training stalls? The figure here shows the minimum required link bandwidth to exchange gradient without stalling training. Here, x-axis shows the gradient size to be exchanged, and the y-axis shows the batch processing time. To exchange gradients without stalls, the model points must be located above these bandwidth lines. However, popular lines like ResNet and VIT require a minimum link bandwidth of more than 1 gigabit per second or 10 gigabit per second, which are far above the WAN bandwidth between Cloud Lab clusters. So, when multiple clusters are connected via WAN, training becomes bottlenecked by insufficient bandwidth and leads to GPU underutilization. This increases training times and cloud costs and makes the overall process inefficient. To overcome such bandwidth limitation, we can use gradient compression to reduce the communication. We can sparsify gradients, which exchange a small fraction of gradient updates. Applying high compression ratio with gradient sparsification can greatly reduce communication time. We can still retain high model accuracy after gradient sparsification, even if we apply high compression ratio of 99%. Several existing work attempt to leverage gradient compression to reduce training time. For instance, ByteDS Compress and HyPress implement efficient compression algorithm on GPU, and Espresso compares and selects optimal compression strategies. However, while these methods showed promise, there are also some limitations. They target a bandwidth of over 25 gigabit per second, a speed that is rarely achievable in multi-cluster settings. This makes this method less applicable or beneficial in our context. Also, techniques used to reduce communication overhead between GPUs bring additional computational overhead. This leads to a trade-off between network load reduction and computational load overhead. The goal of our research is to achieve optimal time to accuracy, or TTA, in a hybrid multi-cluster environment. TTA can be further broken down as the reciprocal of the product of iteration speed and convergence speed. Iteration speed represents the throughput of each batch processed by the GPU. Ideally, this should be bound by the GPU throughput. However, in a situation where the network link bandwidth is insufficient or gradient compression is insufficient, it may become the limiting factor. On the other hand, convergence speed is a factor that shows how the gradient inaccuracy slows down the model convergence. Techniques like gradient compression and applying model stainless can improve the iteration speed, but at the expense of reducing the convergence speed. Balancing these two speeds to optimize CTA is the essence of our design goal. To minimize overall TTA, we explore new strategies and revisit existing solutions. We first explore techniques that optimize training pipeline, which can greatly enhance the iteration speed without adversely affecting the convergence speed. Then we explore strategies like gradient compression, batch size, and staleness, which may have impact on both iteration speed and convergence speed. I'll first discuss strategies that optimize the training pipeline. When we train models with consumer-grade GPUs using existing training pipelines, GPU needs to first compute forward and backward passes, and then compress gradients after the backward pass, as we cannot pipeline backward pass and compression. And GPUs needs to wait communication between nodes to be finished. Finally, GPUs run optimizer after the gradient aggregation. This pipeline leaves GPU idle for a significant amount of time, making train time much longer. One opportunity we can leverage is that we find a larger room for greater involvement of the CPU. In our lab-scale cluster context, CPU plays a pivotal role in gradient transfer, as consumer-grade GPUs do not support direct GPU-to-GPU copy between remote nodes. Instead, gradient must be first copied into the CPU RAM via PCIe lanes. This implies that the model's gradient already exists in the CPU's RAM, so we expect no additional cost for copying gradient from GPU to CPU when we offload tasks such as gradient compression and model optimization. This could potentially free up the GPU for more intensive computational tasks, thereby improving computational and overall efficiency. Taking advantage of the opportunity for greater CPU involvement, we can leverage both the GPU and the CPU to maximize iteration speed and achieve full GPU utilization. We let GPUs to perform computationally intensive forward and backward passes, and let CPU to take care of gradient compression, optimization, and gradient exchange. We adopt a bounded degree of staleness so that GPU can process to next iteration without waiting for communication to be finished. By adopting bounded staleness and pipelining among these training subtasks, we can keep both CPU and GPU fully utilized and synchronized, which in turn improves training efficiency. Top K compression is one of the most widely used methods of gradient sparsification, which selects the top K gradient elements in magnitude. However, in fact, this approach is compute-intensive, as it requires partial sort such as quick select. Threshold V compression can be an alternative for top K. In this method, a threshold V is estimated so that only K elements have a magnitude larger than V. This approach eliminates the need for sorting, greatly reducing the computational burden. This is particularly advantageous at high compression ratios. For example, at a compression ratio of 99%, threshold V compression can reduce the time taken from 1.7 seconds to just 53 milliseconds, which is a significant decrease in computational time. Note that the y-axis is in the log scale. Our second opportunity comes from leveraging the sparsity of gradients. We observe that when model optimization is performed on the CPU, the time taken for the optimization is not negligible compared to the time for forward and backward passes on the GPU. Existing naive approach to update the model with sparsified gradient decompresses the compressed gradient into a dense matrix and using an ordinary optimizer to update the model. However, this introduced too many computations, increasing the processing time. A potential solution is to selectively update only the parameters whose gradient exists in the sparsified gradient. This approach significantly reduces the computational load by avoiding unnecessary updates. We call this sparse optimizer. In action, the sparse optimizer effectively reduces the number of computations for the optimization. However, it is important to note that a 99% compression ratio does not directly translate to a 99% reduction in optimization time. The reason behind this is the way we handle highly sparsified gradients. In such scenarios, we usually need only a single element at a time from each CPU cache line. This leads to frequent pipeline stalls and long waits for DRAM access. Thus, although we are significantly reducing the number of computations, we are not achieving a proportional decrease in optimization time due to these pipeline stalls. Given the limitations of standard sparse optimizer, we propose an improvement, a cache-aware version of gradient compression and optimizer. We introduce cache awareness at the compression stage. Instead of simply selecting top K elements, we select the top K divided by 16 blocks, each block containing 16 elements. Elements selected as such ensures full utilization of all elements that are loaded into the cache when the optimizer runs. This effectively increases the cache hit ratio and reduces the frequency of CPU pipeline stalls. As a result, our cache-aware sparse optimizer experiences a significant speedup. Our evaluation shows the sparse optimizer is up to 17 times faster when introducing cache-aware compression, matching or exceeding the speed of GPU-based dense optimizers. Furthermore, cache-order compression also accelerates compression by itself by 3.4 times. This approach enables CPU-GPU cooperation, maximizing iteration speed and achieving full GPU utilization. Now, I'll discuss strategies for holistic TTA minimization. Another opportunity for improvement lies in reconsidering the per-device batch size. Many previous studies have used adaptive batch sizes as a solution to address Stragler's problem. That is, the entire training time depends on the slowest GPU. This can be a problem, especially when accelerating training with heterogeneous GPU clusters. However, changing the per-device batch size may help balance the computational and communication load. For example, if we use small batch size, we have only small communication time budget and requires frequent optimization. This potentially increases the load of the communication. On the other hand, if we use large batch size, we have greater communication time budget and infrequent optimization, but this risks staleness. This provides an opportunity to use the per-device batch size as a tunable parameter for optimizing time to accuracy. Again, our goal is to optimize TTA in a hybrid multi-cluster environment, so we need to co-optimize both iteration and convergence speed. We need to identify the optimal point where the product of the iteration speed and convergence speed is maximized. To maximize the iteration speed, we first model the iteration speed of each GPU using the Rookfly model. When the per-device batch size is smaller than a certain threshold alpha, the GPUs are not fully utilized due to lower occupancy. The iteration speed linearly increases with the batch size until reaching a saturation point beta. Each GPU and model have different batch size that saturates GPUs and different throughput when saturated. Since the overall iteration speed is determined by the slowest device, we aim to minimize iteration time discrepancies across GPUs. This maximizes the GPU utilization for clusters with heterogeneous GPUs. To maximize convergence speed, we aim to minimize additional training epochs required to achieve the same accuracy. To estimate the number of additional training epochs, we leverage the surrogate model G-bar, which was obtained from Bayesian optimization. We run a few probe training steps with different combinations of batch size and compression ratio to find the surrogate model. Finally, to prevent slowdown due to scarce network bandwidth, we need to impose constraint on the gradient compression ratio. The compression ratio must be large enough not to bottleneck training, given environment variables including link bandwidth, model size, and batch processing time. And the configuration should be dynamically adjusted based on the change in the environment. Please refer to the paper for more details. We implement a centralized controller that collects telemetry data from GPUs and determines the optimal configuration of compression ratio and batch size to minimize TTA. First, the controller loads a model profile obtained via offline profiling. The controller collects the telemetry data from each worker and estimates the performance of each GPU and the network bandwidth. Then the controller makes optimization with respect to the compression rate and per-device batch size based on the telemetry and the model profile. The updated configuration is applied to the workers asynchronously. We evaluate Celatrain under a multi-cluster scenario with an average fluctuating link bandwidth of 115 megabits per second. Celatrain is significantly faster than existing compressed and uncompressed systems and achieves to 104 times faster TTA than PyTorch. We also show that Celatrain dynamically adjusts compression rate and batch size based on the bandwidth, achieving higher iteration speed. Celatrain can reduce cloud costs by 64% and training time by 29% by leveraging a combination of public cloud and on-premise clusters. Compared to using only 6 on-premises GPUs or only 8 cloud GPUs, it is much faster and cheaper to utilize both resources powered by Celatrain. This approach will be beneficial for researchers who want to augment their on-premises computing resources with public cloud resources. To summarize, Celatrain takes a holistic approach to accelerate model training in consumer-grade GPU clusters by co-optimizing several acceleration techniques. Celatrain can accelerate training in multi-cluster settings with limited bandwidth, while also adapting to bandwidth fluctuations. Thank you for listening.